Okay, let's look at P3.32. We are going to plot a potential. We call it a Lennard-Jones potential, where A and B are positive constant, where A and B are this value. There are two parts. The part A is plot this curve, okay, and on a second y-axis on the same figure, plot this curve. It asks you to plot the interesting part of this curve. First of all, you need to know what is Lennard-Jones potential. If you do not know, please Google it. Okay, and then we do part B, where the displacement is small from the equilibrium, can be equivalent to this equation, and you plot it on the same diagram. So let's look at the solution. First of all, you need to import a matplot library and NumPy, and we're going to define the constant. The constants are given in the questions. Okay, it asks you to divide by Boltzmann constant so that the graph is easier to be displayed. When you divide by A and B with a Boltzmann constant, okay, you get unit Kelvin. Here A stroke equal K hyphen B. Actually means that A equal to A divided KB. This means divide by itself. So B stroke equal KP is B equal to B divided KP. Okay, this is important for a short form. Next, you're going to define the function. Okay, in order to define a function, you use DEF. Okay, U is a name, R is a parameter. Okay, this is tell you what is this function mean. Return. So this equation is given by textbook. The same thing. F or F R is parameter. F is the name of the function. So return this one, which is given by the equation. So when you put a value here, so you return, you calculate using this equation, return the value based on this equation. Next, you want to plot a graph, so you need to generate points. So np.linspace generate point from 0.3 to 0.7. In between is 1000 points. Okay, and then I assign u values as ur is the function, f value f u fr. The r is already has a value, so if I put here r, let me run first. Okay, r, you see that 0.7, you see, is the last value, and 0.3. So we generate 1000 value between that. So R is an array of numbers between 0.3 to 0.7 in nanometer. So U values and F values are also array of value. So if you put it here, you generate all the calculated values for each R value display. The same thing happen for the F values. You will generate all the F value for each corresponding R value. So we got a list of values, array of value of U values and F values. So I need to find out the minimum potential energy, because this is U, it must the curve must have minimum potential energy. So the command to rho A is np dot r min, with the index of minimum values along an axis. Okay, so the axis is not just a list of values, array. Okay, so you return the index where the minimum value of U values occur. So if I take min index, the index happened at 204. So U values is minimum at index 204. So if I put U value (204), I get this minimum value of U value. Of course, I need to know what is the epsilon. So U value, minimum index. So this is a epsilon value, the depth potential, and then R is the distance between two atoms. So I know what is the mean index, so corresponding R mean index can be known. So R204 is assess the element inside the array. So it's 0.38. So the key of finding this minimum value is here, is important part. And the next question asks me to calculate the approximate harmonic potential given by K and V values. These are the equation. Now I want to plot the graph. So PLT subplot figure size 8 to 6, which means it's the size of the figure. It turns with a figure and an axis 1. So I'll plot the curve for the UR Lennard-Jones potential. I define color as a red. So my x-axis label is of course R. My y-axis label is the potential in Kelvin, color of red. I'll plot the curve R U, the color red label. Then I plot the take parameters, okay, which is y. Make sure the grade is true. So you can see that there is a lot of command are linked to the matplot library. You go to the matplot library manual. Okay, you can see there are a lot of functions linked to the matplot library. For example, I go to take parameters. What does it mean? So you can see that change the apparent text, take label and grid sign. So it's important to learn how to read. So the manual, so it take in the parameters. So there's like example. It's important to spend some time to read the manual. So I need to create a second graph for the force using the same x-axis. So the twin x is common. I create a second y-axis for the force, but I have to use the same x-axis. So this is common. So the second x-axis with the same interval with the first x-axis. So the color is blue. Okay, and then I want to plot the limit, because or else the curve would not be easily be seen clearly. So I set the y limit, the y-axis limit, from the minimum to the maximum, because the epsilon is the depth of the potential. I want to show it slightly more, so the minimum is times 1.5, maximum potential u value at times 0.5. Okay, the same thing can be done for the second axis, minimum force times 1.5, so that I can some space, and maximum F value. I can plot the harmonic approximation R and V values. Of course, I can add text to the highlight the location of R0, and epsilon. So I give epsilon in 3 decimal places in Kelvin, and then R0 in 3 decimal places. On the right bottom, right font size for color. Of course, I can also put a title for the curve and a legend describing the lines, what is it referring to. So when a graph, these are the legend: FR force, Lennard-Jones potential, harmonic approximation. Those are the legends which you define as labels. Okay, you have labels. Labels are the legend. I show you where I should locate it, how clear I should, how big I should create. The PLD will show the graph. I can see it when you run the program. You can see the curve. The red one is the Lennard-Jones potential. It go from it's negative, go to a minimum negative, and then when you come closer to atom closer, it become repulsive. So repulsive and below negative is attractive force. So of course, potential and force are related. So you can also plot the force. You can see that the force is negative, which is attractive. When it is minimum, the force is the blue line. Okay, blue line. So the zero, when it is zero here, is minimum. The potential is minimum. So then become positive. And then harmonic potential when the located equilibrium, and there's like when you push the atom slightly away the potential. So you can approximate this harmonic approximation, which is somewhat a quadratic approximation.